Welcome back to G Fun Facts Online. Today we are stripping away the sequins, the music, and the applause to look at the cold, hard engine running beneath the world's most beautiful sports. We are talking about the mathematics of perfection. When you watch the Olympics, you see a figure skater land a jump, or a diver slice through the water, and moments later, a number appears on the screen: 15.466, 92.00. To the casual fan, these numbers feel like final verdicts, handed down from on high. But to a mathematician, they are the output of a complex, controversial, and constantly evolving function designed to quantify the unquantifiable. Subjective sports like gymnastics, diving, and figure skating exist at a precarious intersection of art and physics. Unlike a 100-meter dash, where the clock is the only judge, victory here depends on translating aesthetic beauty and biomechanical precision into data. This isn't just a matter of opinion. It is a sophisticated exercise in applied mathematics, robust statistics, and psychology. It is a system built to tame the chaos of human judgment with the order of algorithms. Over the next 20 minutes, we are going to break down the equations, the error margins, the scandals, and the science behind the quest to measure the perfect performance. Let's begin with part 1, the equation of difficulty. The fundamental problem in judging these sports is comparing apples to oranges. How do you weigh a flawlessly executed simple move against a slightly flawed but incredibly dangerous one? The answer lies in the bifurcation of scoring, the separation of difficulty, which is what you attempt, from execution, which is how well you do it. This separation is the bedrock of modern judging, but the mathematics of calculating difficulty varies wildly across disciplines. Let's look at diving. In the world of diving, difficulty is not a feeling, it is an algebraic recipe. The Fédération Internationale de Natation, or FINA, uses a precise formula to assign a degree of difficulty, or DD, to every possible dive. This prevents a judge from arbitrarily deciding that a backflip is hard. The formula for the degree of difficulty on a springboard is actually a summation equation. D equals A plus B plus C plus D plus E. Each variable represents a component of the dive's complexity. A represents somersaults. This is the core engine of the score. A simple 1 somersault might be worth 1.2, while a 4.5 somersaults, known as the quad, rockets the value up to 3.8 or higher. B represents flight position. This is the shape the body takes in the air. A pike, where the legs are straight and the body is bent at the waist, is mechanically harder to rotate than a tuck, which is a ball shape. Therefore, a pike earns a higher value in the equation. A straight position is the hardest of all. C represents twists, or rotations around the body's longitudinal axis. Each half twist adds a specific value, escalating non-linearly as the number of twists increases. D represents the approach. Forward, back, reverse, inward, or arm stand. Approaches where the diver cannot see the water, like reverse or inward, often carry a blind entry premium. And finally, E represents unnatural entry, a variable used for dives that force the body into mechanically disadvantaged positions upon hitting the water. This additive model ensures that a diver can mathematically construct their score before they even step onto the board. If a diver selects a forward 2.5 somersault with 1 twist in a pike position, they are essentially submitting an equation to the judges. If the variables sum to a D of 3.0, that number becomes a multiplier. And this is crucial. The scoring formula for a single dive is the sum of the middle 3 execution scores multiplied by the degree of difficulty. This multiplicative relationship means that difficulty acts as a massive lever. A diver with a high DD of 3.8 can afford lower execution scores and still mathematically beat a diver with a low DD of 2.0 who dives perfectly. This mathematical reality drove the arms race in diving, pushing athletes to attempt the physically impossible to maximize the multiplier. Now, let's contrast this with gymnastics. For decades, gymnastics was defined by the perfect 10. It was a closed system. 10.0 was the ceiling, representing flawlessness. But mathematically, a closed scale creates a compression problem. If a simple routine performed perfectly gets a 10, and a suicidal routine performed perfectly gets a 10, there is no numerical incentive to take risks. The paradigm shifted after the 2004 Athens Olympics, leading to the creation of the open-ended code of points. The perfect 10 was dead. In its place arose 2 separate scores. First, the D score, or difficulty. This score has no ceiling. It is a cumulative sum of the top 8 or 10 most difficult skills performed, plus connection values, which are bonus points for linking difficult moves. Mathematically, if a gymnast performs a Yurchenko double pike vault, known as the Biles 2, it has a massive fixed D score, for example 6.4. A simpler vault might be a 4.6. The gymnast starts with a 1.8 point advantage solely based on the physics of the chosen skill. The second score is the E score, or execution. This remains a closed scale, starting at 10.0 and counting down. Every bent knee subtracts 0.1, every wobble subtracts 0.3, and every fall subtracts 1.0. The final score is simple addition. D-score plus E-score. This additive model fundamentally changed the sport. In a multiplicative system like diving, a fall on a hard skill destroys the score because the multiplier applies to a small execution number. In the additive gymnastics model, a gymnast can fall, losing 1.0 from their E-score, but still win if their D-score is 1.5 points higher than their competitors. The math favors power gymnastics, high difficulty, even with imperfections, over safe artistic perfection. Then we have figure skating, which uses the International Judging System, or IJS. This is perhaps the most mathematically granular of all. Every single movement on the ice, from a quad lutz to a step sequence, is assigned a code and a base value. For instance, a quad lutz might have a base value of 11.50, while a triple axel is around 8.00. A skater's program is essentially a spreadsheet. The technical panel identifies the content, the rows of the spreadsheet, and the judges fill in the quality column, known as the grade of execution, or GOE. The GOE is not just a point added, it is a percentage function. A +5 GOE adds 50% of the element's base value, while a -5 cuts it significantly. This creates a risk-reward matrix. If you land a quad lutz perfectly, you earn the 11.50 base plus half of that again, totaling 17.25 points. If you fall on that same jump, receiving a -5 GOE and a 1.0 deduction, your score drops to 4.75 points. Compare this to a safe triple lutz with a base value of 5.90. Even executed perfectly, it maxes out around 8.85 points. The math dictates the strategy. The potential upside of the quad is so high that the expected value, in a probabilistic sense, of attempting it often outweighs the safe alternative, even with a high probability of failure. This mathematical structure has single-handedly revolutionized skating, turning it into a jumping contest where the base value column often determines the winner before the music even starts. Part 2. The statistics of consensus. Once difficulty is established, the judges must evaluate execution. This is where subjectivity enters. To prevent one rogue judge from fixing a competition, sports federations rely on robust statistics. The primary tool is the trimmed mean. In a standard Olympic panel, you might have 9 judges. If all 9 judges score a skater, the system does not simply average them. First, it drops the highs and lows. The highest score and the lowest score are discarded. Sometimes the 2 highest and 2 lowest are dropped. Then, the remaining scores are averaged. The mathematical justification for the trimmed mean is resistance to outliers. In statistics, the mean, or average, is highly sensitive to extreme values. If 8 judges give a 9.0 and 1 corrupt judge gives a 2.0, a simple average drops to 8.2, which is a massive penalty. With a trimmed mean, the 2.0 is discarded entirely. The score remains 9.0. This protects against 2 things: corruption, where a judge tries to tank a rival, and incompetence, where a judge simply misses an angle. Furthermore, judging panels are monitored using deviation analysis. After a competition, statisticians analyze how often a specific judge's scores fell inside the corridor, the range defined by the trimmed mean of their peers. If Judge A is consistently 0.5 points higher than the trimmed mean of the panel, they are flagged for nationalistic bias or general incompetence. This statistical oversight is the police force of subjective sports, using standard deviations to enforce objectivity. Part 3. The psychology of the number. Even with trimmed means and difficulty formulas, the input, the score itself, comes from a human brain. And the human brain is a terrible statistical instrument. It is riddled with cognitive biases that no formula can fully erase. First, there is the halo effect. Psychologists have long documented this phenomenon, where a positive impression in one area bleeds into another. In sports, this manifests as reputation bias. A legendary skater or gymnast steps onto the floor with a halo. Judges expect perfection. If a legend has a minor wobble, the brain, primed for greatness, might subconsciously smooth it over, scoring at a 9.2, where an unknown rookie would get an 8.8. This creates a scoring inertia. It takes a massive error to break the halo, while new athletes must perform exponentially better to build one. Second, we have the serial position effect, or order bias. In almost every subjective sport, it is statistically better to go last. Data analysis consistently shows a positive drift in scores as an event progresses. There is the warm-up effect, where judges are conservative early in the competition to save room in case a later skater is brilliant. If they give the first skater a 9.5 and the last skater is better, they have nowhere to go. Then there is recency bias. The last performance is the freshest in memory. A study of gymnastics scores showed that for every position later in the lineup a gymnast performs, their score increases by roughly 0.02 to 0.05 points, independent of actual performance quality. In a sport decided by thousandths of a point, the random draw of starting order is a significant statistical variable. Third is conformity bias. Judges are social creatures. In systems where judges' scores are visible to each other, there is a subconscious pressure to conform. If a judge sees that the respected head judge gave a 9.0, and they were thinking 8.5, they might panic and adjust up. Modern systems try to combat this with blind scoring, but post-competition analysis can paradoxically encourage conformity. If you are punished for being an outlier, your mathematical survival strategy is to guess what everyone else will score, rather than score what you see. This is the Keynesian beauty contest of sports judging. Finally, the elephant in the room, nationalistic bias. Studies analyzing figure skating scores have found clear evidence that judges score athletes from their own country significantly higher. This often manifests as vote trading, or block judging. The French judge helps the Russian pair, and the Russian judge helps the French ice dancers. This bias leaves a statistical fingerprint. When a judge's deviation favors a specific country, only when that country's medal hopes are at stake, it suggests strategic, rather than random, variation. Part 4. The scandal that changed the math. The history of sports judging is divided into two eras, before 2002 and after 2002. The catalyst was the Salt Lake City Olympics. In the pairs figure skating final, the Russian pair, Berezhnaya and Sikharulidze, made a clear technical error. The Canadian pair, Sale and Pelletier, skated flawlessly. The world expected gold for Canada. But when the scores came up, the Russians won, 5 judges to 4. The French judge later alleged she had been pressured to vote for the Russians. The scandal shattered the credibility of the sport. This marked the death of the 6.0 system. The International Skating Union realized the old ranking system was mathematically broken because it was opaque. A 5.8 meant nothing intrinsically, it only meant worse than 5.9. The solution was the IJS, or Code of Points. The system shifted from ordinal ranking to cardinal scoring. You don't just place first, you earn 150.25 points. By breaking a performance into distinct elements with granular base values, the IJS forces judges to justify the math. You can't just feel a win, you have to find the points in the spreadsheet. Part 5. The Modern Era. In the wake of skating's revolution, other sports tightened their math. Artistic swimming, formerly known as synchro, introduced a radical new system for the 2024 Paris cycle. Coaches must now submit a menu of their routine's difficulty before the meet, known as the coach card. They declare their difficulty. A new panel of officials called technical controllers watches only to see if the declared difficulty was actually performed. If a swimmer declares a hybrid sequence with a difficulty of 3.5 but misses a rotation, the technical controller hits a button. The difficulty doesn't just drop slightly, it drops to a base mark, often 0.5. This introduces a binary risk. In the past, a small error meant a small deduction. Now a small error triggers a massive difficulty reset. The scoring function has become discontinuous. It is a step function where a millimeter of error causes a cliff drop in points. Part 6. Future Trends and the Rise of the Machine. The ultimate solution to human bias is to remove the human. AI judging is no longer science fiction. In 2019, the International Gymnastics Federation began testing a laser-based system developed by Fujitsu. 3D laser sensors track the gymnast's skeleton 2 million times per second. This is the geometry of truth. The AI knows exactly if a split leap was 180 degrees or 178 degrees. It knows if a handstand was within 2 degrees of vertical. Currently, the AI is a judging support system. It provides the difficulty score and handles objective angle deductions, while humans still judge artistry and flow. Similarly, computer vision in diving and skating is being trained to recognize splash size or ice coverage and rotation speed. The math is moving from human approximation to pixel-perfect measurement. But this brings us to a philosophical cost. As we approach mathematical perfection, do we lose the art? A human judge might forgive a 179-degree split because the musicality was breathtaking. An AI sees only a -0.1 deduction. The digitization of subjective sports pushes athletes toward robotic perfection, maximizing the variables that the algorithm can see, perhaps at the expense of the soul that the audience feels. In conclusion, we score subjective sports because we crave a hierarchy of excellence. We want to know who is the best. The mathematics of judging, from the quadratic equations of diving difficulty to the trimmed means of execution, is our attempt to build a ladder to that truth. It is an imperfect science. The score will never be as absolute as the time on a stopwatch. There will always be a ghost in the machine, the bias of the observer, the angle of the view, the lingering memory of a past champion. But the evolution of these systems tells the story of sport itself. It is the relentless pursuit of fairness in an unfair world, using the only universal language we have, math. We may never reach scoring perfection, but like the athletes themselves, the numbers will keep trying to stick the landing. Thanks for listening to G Fun Facts Online.